Welcome to the world of digital electronics, where logic meets innovation to power modern technology. In this section, we move into sequential logic circuits. Sequential logic design means logic with memory. Unlike combinational circuits, the output here does not depend only on current inputs. Oh no, it also depends on the previous state stored inside memory elements. These memory elements are implemented using latches and flip-flops. Now, let's look at the core building blocks. First, the state element. This is the memory part of the system. We have latches, which are level sensitive, and flip-flops, which are edge-triggered. Among them, the D flip-flop is the most commonly used in modern digital systems. Next, we have the combinational next state logic. This block computes the next state, typically the D input of a flip-flop, using the present state and current inputs. Finally, the output logic computes the final outputs. These outputs are derived from the stored state and sometimes directly from inputs as well. Together, these blocks form the foundation of all sequential digital systems, including counters, registers, and finite state machines. Now, let's understand how sequential logic circuits are usually built. First, remember this idea. Sequential circuits have memory. So, the circuit remembers what happened before, and that stored value is called the present state. Typical structure. Now, the circuit calculates the next state. We write it like this. Next state equals function of present state inputs. Meaning, we examine the current stored state. We analyze the current inputs, and then we determine what the next stored value ought to be. Now, what about the outputs? There are two common ways. A Moore machine. In a Moore machine, the output depends solely on the present state. So even if inputs change, the output changes only when the state changes. Now, let's talk about the Mealy machine. In a Mealy machine, the output depends on both the present state and the inputs. Thus, here, the output can change immediately when the inputs change. Now, let's look at common sequential circuits you will see in digital design. 1. Registers. A register stores multiple bits, like 8-bit, 16-bit, 32-bit storage. 2. Shift registers. A shift register moves data left or right, 1 bit per clock, used for serial to parallel conversion, parallel to serial conversion, adding delays in digital systems. 3. Counters. A counter counts clock pulses. Up counter 1, 2, 3. Down counter 3, 2, 1, 0. Mod N counter counts only up to n-1 and repeats. Ring and Johnson counters are special counter types used in timing and sequencing. 4. FSM finite state machine. An FSM is like a step-by-step controller. Example, traffic light controller, vending machine logic, CPU control unit. FSM decides what state you are in now, what state to go next, what output to generate. 5. Synchronizers. Sometimes signals come from outside and are not aligned with the clock. So we use synchronizers to make them safe. A common one is the 2 flip-flop synchronizer to reduce metastability risk. 6. Timers, dividers, pulse generators, used to create delays, slower clocks, pulses of required width. 7. Sequence detectors. These detect a pattern, like 1011 in a serial input stream. 8. Memory interface control. When working with RAM or FIFO, we need control logic for read enable, write enable, full empty checks. That control is mainly sequential logic. So, overall, sequential logic circuits are the building blocks for storage, counting, timing, and control. Use everywhere, from small digital circuits to complete processors and SoCs. Let's quickly understand the difference between combinational logic and sequential logic. This is one of the most important concepts in digital electronics. First, combinational logic. Combinational logic depends only on the current inputs. If the inputs change, the output changes immediately after a small delay. There is no memory inside. Examples: adders, multiplexers, decoders, comparators. Now, sequential logic. Sequential logic depends on current inputs and past state. That means it has memory. It uses latches, flip-flops, and registers to store information. Another key difference: the clock. Combinational logic does not need a clock. Sequential logic usually works with a clock signal. Outputs change at clock edges, making the system synchronized and predictable. In combinational design, we focus on Boolean equations and K-maps. In sequential design, we work with state diagrams, timing constraints, setup, and hold time. So, here's the simplest way to remember it. Combinational logic computes. Sequential logic remembers and controls. And together, they form the backbone of every processor, controller, and digital system you use today. Now, let's understand what is a latch. A latch is a level-sensitive, 1-bit memory element. That means it can store 1 bit of information at its output, which we call Q. A latch has an enable signal, also called E. Sometimes you may hear it referred to as gate or even clock. But for a latch, we usually say enable. Here is the key idea. When enable is active, for an active high latch, that means E equals 1. The latch becomes transparent. Transparent means the output is not locked. So Q follows the input. In a D latch, the input is D, so when E is 1, we say Q equals D. Now, when enable becomes inactive, meaning E equals 0, the latch is no longer transparent. It stores the last value and holds it. So even if D changes, the output Q remains constant because the latch is holding the previous stored value. So remember these two lines. E equals 1, Q follows D. E equals 0, Q holds the previous value. This behavior is called D-latch behavior, and it's the most common latch used in digital design. Now let's learn the SR latch. SR means set-reset, and it's the simplest 1-bit memory element in sequential logic. It is built using 2 cross-coupled gates, and it stores 1 bit at the outputs Q and Q bar. It has 2 control inputs. S stands for set. It makes Q equal to 1. R stands for reset. It makes Q equal to 0. Now let's understand the truth table for the NOR-based SR latch. When S equals 0 and R equals 0, the latch does not change. It simply holds the previous value. So we call it the memory or hold state. When S equals 1 and R equals 0, the latch goes to the set state. So Q becomes 1. When S equals 0 and R equals 1, the latch goes to the reset state. So Q becomes 0. Now the important case. When S equals 1 and R equals 1, this is invalid or forbidden for a NOR SR latch. Because both NOR gate outputs get forced to 0, Q and Q bar become the same, which breaks the basic rule that they must be complements. And when S and R return back to 0, the final stored state can become unpredictable. That's why we avoid this input combination in real designs. So remember, 0, 0, hold, 10 set, 01 reset, 11 invalid. This SR latch is the base concept. From here, we build safer latches like the D latch. Here, you can see two NOR gates. Notice something important. The output of each gate is connected back to the other gate. This is called cross-coupling. That feedback connection is what allows the circuit to remember a value. Without feedback, there is no memory. On the left side, we have two inputs. S means set, R means reset. On the right side, we have two outputs, Q and Q bar, which is the complement of Q. Now, let's go step by step through each case. First case. When S equals 0 and R equals 0, neither gate is forcing the output. So, the latch simply keeps whatever value it had before. This is called the hold or memory state. Second case. When S equals 1 and R equals 0, the lower NOR gate forces its output to 0. Because of feedback, the upper gate output becomes 1. So, finally, Q becomes 1. We call this the set state. Third case, when S equals 0 and R equals 1. Now, the upper NOR gate forces its output to 0 through feedback. The lower gate output becomes 1, so finally, Q becomes 0. This is called the reset state. Now, the important warning case. When S equals 1 and R equals 1, both NOR outputs go to 0. That makes Q and Q bar equal, which breaks the rule that they must be opposites. When we release both inputs back to 0, the final state can become unpredictable, so we call this input combination invalid. So remember, two cross-connected NOR gates plus feedback gives us the simplest 1-bit memory element, the SR latch. Let's understand the SR latch waveform step by step. We are given input waveforms for S and R, and we need to draw the outputs Q and Q bar. We are also told that the propagation delay of each NOR gate is 10 nanoseconds. That means whenever S or R changes, the output will respond after 10 nanoseconds, not instantly. First, let's remember the behavior of the SR latch. If S pulses high, Q becomes 1. This is the set operation. If R pulses high, Q becomes 0. This is the reset operation. If S equals 0 and R equals 0, the latch holds its previous value. If S and R go high together, that is an invalid condition. Now, look at the waveform. When the first S pulse goes high, after a 10 nanosecond delay, Q becomes 1. At the same time, Q bar becomes 0. When S returns to 0 and R is still 0, the latch simply holds the value. Q stays at 1. Next, when the R signal goes high, after a 10 nanosecond delay, Q goes to 0, and Q bar becomes 1. Again, when both S and R return to 0, the latch holds the new value. Now, notice, if S and R ever go high at the same time, both outputs temporarily go low in a NOR latch. When they return to 0, the final state can become unpredictable. That is the invalid region. So, when reading SR latch waveforms, remember this simple rule. S pulse, set, Q becomes 1. R pulse, reset, Q becomes 0. S equals R equals 0, hold. S equals R equals 1, invalid. And always account for the propagation delay when drawing outputs. Let's understand the JK latch. A JK latch is a level-sensitive latch, which means it works using an enable signal, E. When E is active, the latch can respond to inputs. When E is inactive, the latch holds its previous output. The JK latch is an improved version of the SR latch. In the SR latch, the case S equals 1 and R equals 1 is invalid. But the JK latch removes that forbidden condition and replaces it with a useful operation called toggle. Now, let's take a moment to examine the truth table. When J equals 0 and K equals 0, there's absolutely no change. So, the output Q maintains its previous value. Next, when j equals 0 and k equals 1, the latch executes a reset. Consequently, q becomes 0. In the case where j equals 1 and k equals 0, the latch performs a set. Therefore, q becomes 1. Now, let's discuss the most crucial scenario. When j equals 1 and k equals 1, the jk latch toggles. This means if q was 0, it transforms into 1, and if q was 1, it flips to 0. Hence, q becomes q bar. That's why jk is important. It transforms the invalid SR case into a highly useful toggle action. So remember this: 0, 0, hold, 0, 1, reset, 1, 0, set, 1, 1, toggle. This is the JK latch, and later we will explore the JK flip-flop, which is clock edge controlled and effectively solves race issues. True. Let's understand the JK latch. A JK latch is a level-sensitive latch, which means it works using an enable signal, E. When E is active, the latch can respond to inputs. When E is inactive, the latch holds its previous output. The JK latch is an improved version of the SR latch. In the SR latch, the case S equals 1 and R equals 1 is invalid. But the JK latch removes that forbidden condition and replaces it with a useful operation called toggle. Now, let's take a moment to examine the truth table. When j equals 0 and k equals 0, there's absolutely no change. So, the output q maintains its previous value. Next, when j equals 0 and k equals 1, the latch executes a reset. Consequently, q becomes 0. In the case where j equals 1 and k equals 0, the latch performs a set. Therefore, q becomes 1. Now, let's discuss the most crucial scenario. When j equals 1 and k equals 1, the jk latch toggles. This means if q was 0, it transforms into 1, and if q was 1, it flips to 0. Hence, q becomes q bar. That's why jk is important. It transforms the invalid SR case into a highly useful toggle action. So remember this: 0, 0, hold, 0, 1, reset, 1, 0, set, 1, 1, toggle. This is the JK latch, and later we will explore the JK flip-flop, which is clock edge controlled and effectively solves race issues. True. Let's quickly understand the JK latch waveform. Here you can see J, K, the enable signal, and the output Q. Remember, this is a level-sensitive latch, so when enable is 1, the latch responds to J and K. When enable is 0, the latch simply holds its value. Now look at the cases. When J is 1 and K is 0, Q goes to 1. That's set. When j is 0 and k is 1, q goes to 0. That's reset. When j is 0 and k is 0, q stays the same, hold. And when j is 1 and k is 1, q toggles. It flips to the opposite value. So as you move along the waveform, just check j and k, while enable is high. That tells you exactly what q will do. Simple rule: set, reset, hold, toggle. Let's discuss the primary concern with the JK latch, the race-around condition. Keep in mind, a JK latch is level-sensitive. Therefore, while enable E is high, the latch remains transparent and feedback is active. Now here is the problem case. If E stays high and J equals K equals 1, the latch is supposed to toggle. But because the output Q is fed back into the circuit and gates have propagation delay, Q may not toggle just once. Instead, it can toggle again and again and again during the same enable high window. So the final value of Q becomes unpredictable. It depends on delays and how long E stays high. That is called the race-around condition. That's why. practical designs avoid using a simple JK latch for toggling. To solve this, we use either an edge-triggered JK flip-flop or a master-slave JK configuration. Both ensure Q changes only once per clock cycle, preventing multiple toggles. So, simple summary: JK latch plus E high plus J equals K equals 1, repeated toggles, race around, use JK flip-flop or master-slave JK. We will discuss JK master-slave flip-flop after all latches. Now, let's understand the D-latch. A D-latch, also called a data or delay latch, is a level-sensitive, sequential circuit that stores one bit of data. The output is Q, along with its complement, Q bar. The key idea is simple. When the enable signal, EN, is active, the latch becomes transparent. That means the output Q directly follows the input D. When EN becomes inactive, the latch stops updating and holds the last stored value. Even if D changes, Q remains constant. The D latch is derived from the SR latch by eliminating the invalid state. In an SR latch, both S and R can accidentally become active at the same time, creating a forbidden condition. The D latch avoids this by generating S and R internally in a controlled way. Inside the circuit, we use an SR latch core along with input logic. The inputs are generated as S equals D and EN, R equals D bar and EN. When EN is high, if D is 1, S becomes 1 and the latch sets, so Q becomes 1. If D is 0, R becomes 1 and the latch resets, so Q becomes 0. When EN is low, both S and R become 0, and the latch simply holds the previous value. So remember the two key rules. EN equals 1, Q follows D. EN equals 0, Q holds the previous value. That is the fundamental behavior of a D latch. We'll understand the D latch using its gate diagram and truth table. On the right side, you can see the D latch built from an SR latch core, along with input logic. The input is D, and the control signal is enable, shown here as click or EN. The outputs are Q and Q bar. The main behavior is simple. When enable is 1, the latch is transparent, so Q follows D. If D is 1, the latch sets and Q becomes 1. If D is 0, the latch resets and Q becomes 0. When enable is 0, the latch is not transparent. It holds the previous value. That means Q stays the same even if D changes. Now confirm this with the truth table. When EN is 0, D can be anything, and Q next equals the previous Q. This is the hold state. When EN is 1 and D is 0, Q next becomes 0. That is reset. When EN is 1 and D is 1, Q next becomes 1. That is set. So remember, enable low means hold. Enable high means Q follows D. That is the D latch operation. Let's quickly review the D latch using this waveform. At the top, we have the enable signal. Below that is the data input D. At the bottom is the output Q. When enable is high, the latch is transparent. That means Q follows D. So whenever D changes while enable is 1, the output changes accordingly. You can see in the waveform that during the high enable window, Q tracks D. Now look at the moment when enable goes low. As soon as enable becomes 0, the latch closes. From that point onward, even if D changes, Q stays constant. This is the latched or hold state. So the simple rule is, enable high, Q follows D. Enable low, Q holds the last value. Now let's understand the T-latch, also called the toggle latch. A T-latch is a level-sensitive sequential circuit. It changes its output only when the enable signal is active. The behavior is very simple. When T is 0, the latch holds its present state. When T is 1, the latch toggles its output, meaning Q flips to the opposite value. In practical designs, a T-latch is commonly built using a D-latch with XOR feedback. The key relationship is D equals T XOR Q. So if T is 0, then D becomes Q, which means no change at the output. If T is 1, then D becomes Q bar, so the output toggles. So remember, with enable active, T equals 0 means hold, and T equals 1 means toggle. That is the basic working of a T-latch. Let's understand the T-latch using its truth table and block diagram. First, T-latch means toggle latch. It is used when we want the output to either hold its value or toggle to the opposite value. In this truth table, we are assuming enable is active, meaning the latch is allowed to update. Look at the first two rows. When T is 0, the output does not change. If Q is 0, it stays 0. If Q is 1, it stays 1. So T equals 0 means hold. Now, look at the next two rows. When T is 1, the output toggles. If Q is 0, it becomes 1. If Q is 1, it becomes 0. So T equals 1 means toggle. Now connect this with the block diagram on the right. You can see an XOR gate feeding a D latch or D flip-flop. One input of the XOR is T, and the other input is the current output Q fed back. So the input to the storage element becomes D equals T XOR Q. If T is 0, D becomes Q, so the output holds. If T is 1, D becomes Q bar, so the output flips. So the simple summary is T equals 0, hold the same output. T equals 1, toggle the output. That is the working of the T-latch. Let's quickly read this T-latch waveform. At the top is enable, EN, then the T input, and at the bottom is the output Q. When enable is high, the latch is active. During this time, if T is 0, Q holds its current value. If T is 1, Q toggles, meaning it flips to the opposite value. You can see that every time T becomes 1 while enable is high, the output Q changes state. When enable goes low, the latch closes, so Q stays fixed even if T changes. So the simple rule is, enable high plus T equals 1 makes Q toggle. Enable low makes Q hold. Now let's compare all common latches in one clear view. First, the SR latch using NOR gates. It has inputs S and R. When enabled, S equals 1 sets Q to 1, and R equals 1 resets Q to 0. But S equals 1 and R equals 1 is invalid. It is the simplest memory element, built using cross-coupled NOR gates. Next, the SR latch using NAND gates. This is the active low version. It behaves similarly, but with inverted inputs. It is commonly used in real circuits with active low control signals. It still has an invalid case. Now the gated SR latch. This adds an enable signal. It behaves like an SR latch only when enable is active, but it still has the forbidden condition inside. Next is the D latch, also called the transparent latch. It has only one data input, D, plus enable. When enable is high, Q follows D. When enable is low, Q holds its last value. There is no invalid case because the internal logic prevents it. This is the most commonly used latch in data paths. Then we have the JK latch. Inputs are J and K with enable. J equals 1 sets, K equals 1 resets, and when J equals K equals 1, it toggles. It removes the invalid SR condition. However, because it is level sensitive, it can suffer from race around if enable stays high. Next is the T latch, or toggle latch. It has a single input P and enable. When T is 0, it holds. When T is 1, it toggles the output. It is often implemented using a D latch with XOR feedback. It can also have race issues if enable stays high too long. Finally, the general enable latch term usually refers to a D latch with an enable input. The output tracks the input while enabled and holds when disabled. So, in summary, SR latch is the simplest but has an invalid state. D latch removes the invalid state and is widely used. JK latch replaces the invalid case with toggle. T latch simplifies toggle behavior. Each latch builds on the previous one to improve reliability and functionality in digital systems. Let's understand the SR flip-flop. An SR flip-flop, which stands for set-reset flip-flop, is a 1-bit memory element with two control inputs, S and R. S is the set input. When S is active, it forces Q to 1. R is the reset input. When R is active, it forces Q to 0. The outputs are Q and its complement, Q bar. One important point, in basic SR designs, one input combination is forbidden or invalid if both set and reset are activated at the same time. The final state becomes unpredictable. Now let's clearly understand the difference between an SR latch and an SR flip-flop. An SR latch is level sensitive. It does not necessarily require a clock, or it may use an enable signal. The output can change whenever the inputs change while enabled. An SR flip-flop is edge-triggered. That means it changes its output only at a clock edge, such as the rising or falling edge. It is usually built using two latches in a master-slave configuration or with an internal edge-triggered structure. So the key difference is latch responds to levels. Flip-flop responds to clock edges. That is the basic idea of the SR flip-flop. This is an edge-triggered SR flip-flop, which means it updates only at a clock edge. For example, at the rising edge of the clock. Conceptually, here's what happens. During the active clock edge, the inputs S and R are sampled. Outside that clock edge, the output Q holds its previous value. So unlike a latch, which responds while enabled, a flip-flop responds only at the instant of the clock transition. Now let's look at the conceptual truth table. If S is 0 and R is 0, then at the clock edge, Q remains the previous value. If S is 1 and R is 0, then at the clock edge, Q becomes 1. That is the set operation. If S is 0 and R is 1, then at the clock edge, Q becomes 0. That is the reset operation. If S is 1 and R is 1 at the clock edge, that is invalid. This is the same forbidden condition we saw in the SR latch. The next state equation summarizes the behavior. Q next equals S plus R bar times Q. One practical note. In real synchronous digital systems, designers usually avoid SR flip-flops because of this invalid case. Instead, they prefer D flip-flops or JK flip-flops. So remember, SR flip-flop updates only at the clock edge, but it still has the invalid input combination. Now let's understand the JK flip-flop. A JK flip-flop is an edge-triggered 1-bit storage element. It improves the SR flip-flop by removing the invalid input condition. In a JK flip-flop, when both inputs are 1, the output toggles instead of becoming invalid. This flip-flop updates only at the active clock edge, for example, at the rising edge of the clock. Now let's go through the truth table at the clock edge. When J is 0 and K is 0, the output does not change. Q next equals Q present. This is the hold condition. When J is 0 and K is 1, the output resets. Q next becomes 0. When J is 1 and K is 0, the output sets. Q next becomes 1. When J is 1 and K is 1, the output toggles. That means Q next becomes the complement of the current Q. The characteristic equation summarizes this behavior. Q next equals J times Q bar plus K bar times Q. So remember, 0, 0 means hold, 0, 1 means reset, 1, 0 means set. 11 means toggle. That is the complete working of the JK flip-flop. To avoid race conditions, which exist in the JK latch, we implement the JK master-slave JK flip-flop. A master-slave JK flip-flop is built using two latches, so people see latch blocks and think it's still a latch. But the combination of two latches with opposite clock phases behaves like an edge-triggered device, so we call the overall thing a flip-flop. Now let's discuss the master-slave JK configuration and why it is important. In a normal JK latch, there is a practical problem called the race-around condition. Because the JK latch is level sensitive, if enable stays high and J equals K equals 1, the output can toggle multiple times due to feedback and gate delays. So the final value of Q becomes unpredictable. To solve this race problem, we use the master-slave JK flip-flop. A master-slave JK flip-flop is built using two level-sensitive latches connected in series. The first latch is called the master latch. It is active when the clock is high, meaning CLK equals 1. So during this time, the master latch captures the effect of J and K. The second latch is called the slave latch. It is active when the clock is low, meaning CLK equals 0, using an inverted clock. Because of this opposite timing, only one latch is active at a time. When the master is open, the slave is closed. When the slave is open, the master is closed. So even if J and K are both 1, the output Q can update only once per clock cycle, not repeatedly. That removes the race-around condition and makes the overall circuit behave like an edge-triggered flip-flop. So the main reason we discuss master-slave JK is simple. JK latch can race when J equals K equals 1, and master-slave design prevents that by allowing only one controlled update per clock cycle. A master-slave JK flip-flop is built using two latches, so people see latch blocks and think it's still a latch. But the combination of two latches with opposite clock phases behaves like an edge-triggered device, so we call the overall thing a flip-flop. In JK master-slave flip-flop using this waveform, at the top is the clock, below that is QM, the master output. At the bottom is QS, the slave output, which is the final output Q. When the clock is high, the master latch is active. During this time, QM can change depending on the J and K inputs. However, the slave latch is closed, so the final output Q does not change yet. When the clock transitions from high to low, the master latch closes and holds its value. At the same moment, the slave latch becomes active and copies the value from the master to the output. That means the final output changes only once per clock cycle, during the clock transition. This structure eliminates the race-around condition that happens in a simple JK latch when J equals K equals 1. So remember, master updates during clock high, slave updates during clock low, and the final output changes only once per clock cycle. A D flip-flop is an edge-triggered 1-bit memory element. It captures the input D only at the active clock edge, either the rising edge or falling edge, depending on the design, and then holds that value until the next clock edge. Looking at the inputs and outputs, the inputs are D and CLK. In many practical circuits, you may also see reset or preset pins. The outputs are Q and Q bar. Now let's understand the operation. On the active clock edge, Q simply takes the value of D. If D is 0 at the clock edge, Q becomes 0. If D is 1 at the clock edge, Q becomes 1. Between clock edges, even if D changes, Q does not change. It holds its previous value. So the key equation is simple. Q next equals D, but only at the clock edge. Let's see why the D flip-flop is the most commonly used storage element in digital design. First, it has no invalid input condition. Unlike the SR flip-flop, there is no forbidden combination because the D flip-flop has only one data input. Second, it has no race-around problem. Unlike a level-sensitive JK latch, the D flip-flop updates only at the clock edge, so the output cannot toggle repeatedly within the same clock window. That's why D flip-flops are perfect building blocks for real systems. They are used to build registers, pipeline stages, counters with some combinational logic, and also to store states in finite-state machines. Now look at the gate-level diagram shown below. Internally, it is built using gating logic and feedback to store one bit reliably. Even though the internal structure uses gates and feedback, the external behavior is simple. At each active clock edge, Q takes the value of D and holds it until the next edge. So the summary is no invalid case, no race around, and very easy to use in synchronous digital systems. That's why the D flip-flop is the most widely used flip-flop. In this slide, we are looking at a D flip-flop with preset and reset control signals. Let's understand how these signals work along with D and clock. Most practical D flip-flops include asynchronous control pins called preset and reset. Reset, also called clear, forces the output Q to 0. Preset, also called set, forces the output Q to 1. The key word here is asynchronous. That means preset and reset work immediately. They do not wait for a clock edge. And they override the D input. So even if the clock is not toggling, if reset is asserted, Q becomes 0 instantly. If preset is asserted, Q becomes 1 instantly. When both preset and reset are inactive, the flip-flop behaves normally. On the active clock edge, Q takes the value of D and holds it until the next clock edge. So in summary, preset and reset give us direct control of the output, while D and clock control the normal synchronous data operation. Now let's understand the T flip-flop. A T flip-flop is an edge-triggered 1-bit storage element. Its operation is very simple. If T is 0, the output holds its current value. There is no change at the clock edge. If T is 1, the output toggles. That means Q flips to the opposite value at every active clock edge. Now confirm this using the truth table. When T is 0, if Q is 0, it stays 0. If Q is 1, it stays 1. So T equals 0 means hold, when T is 1. If Q is 0, it becomes 1. If Q is 1, it becomes 0. So T equals 1 means toggle. The characteristic equation summarizes this. Q next equals Q XOR T. So remember, T equals 0, no change. T equals 1, toggle at every clock edge. That is the basic working of the T flip-flop. Now let's see how we can build a T flip-flop using other flip-flops. There are two common methods. Method A is using a JK flip-flop. We simply connect J and K together and set both equal to T. If T is 0, then J equals K equals 0, so the output holds. If T is 1, then J equals K equals 1, and the flip-flop toggles at every clock edge. So a JK flip-flop naturally becomes a T flip-flop when J and K are tied together. Method B is using a D flip-flop. Here, we feed the D input with Q XOR T. At every clock edge, the value at D is loaded into Q. If T is 0, D equals Q, so no change. If T is 1, D equals Q bar, so the output toggles. So both methods give the same hold and toggle behavior. But using a D flip-flop with XOR feedback is very common in practical designs. Now let's summarize the most common edge-triggered flip-flops. First, the SR flip-flop. It has inputs S and R. On the clock edge, S equals 1 sets the output. R equals 1 resets the output, and both 0 means hold. However, S equals R equals 1 is invalid. Because of this forbidden case, SR flip-flops are rarely used in synchronous design. Next, the JK flip-flop. It improves the SR by removing the invalid condition. When J and K are both 1, the output toggles. There is no forbidden case. It is commonly used in counters, but it requires more internal logic compared to a D flip-flop. Now, the D flip-flop. It has only one data input, D. On the clock edge, Q simply becomes D. There is no invalid case and no ambiguity. That's why D flip-flops are the most widely used in registers, pipelines, and FSM state storage. Finally, the T flip-flop. If T is 0, the output holds. If T is 1, the output toggles at every clock edge. It is commonly used in counters and frequency divider circuits. So in summary, SR is basic but has an invalid case. JK fixes SR. D is the simplest and most practical. T is ideal for toggle and counter applications.